Hi guys, so in this video I'm back with some challenging problems. So guys, we have covered a lot of different techniques and methods and all that. Now I want to just choose some challenging problems, and I want to show you how we can actually work through these challenging problems and how we can find or evaluate the derivative of these functions. Guys, you can already see that this is a function which looks of the form x to the power x. So we can think of this as an exponential function, but then at the same time we cannot really put it into the category of an like an exponential function where we see that b to the power x form or e to the power x form, where we know the base is always like a constant, okay, and x, I mean the exponent, is a variable. Well, in this example we can also not classify this into this the power rule kind of a thing, because, and guys, that is something that I find sometimes students, and probably like even me, when I actually looked at this for the first time as a student, I think I tried to use the power rule on that, but then one has to realize one cannot use the power rule, because guys, power rule works of course for x to the power n type of functions, but n, the exponent, has to be constant. Here guys, exponent is not a constant, it is still a variable. Now it is not, we cannot use the power rule on that. Guys, it is not just our typical exponential function of the form at a constant base to the power variable. It is not a log function, guys. Obviously we cannot classify this into a trig function. So basically we cannot classify this into any of those things that we have, like any of those functions especially that we have already evaluated the derivatives for. Guys, actually these functions, and even for that matter the trig functions and the other exponential functions, guys, they come under a different set of functions which are also sometimes called as the transcendental functions. I'm not going to go into a lot of details about what exactly are the transcendental functions, but guys, I just still wanted to share with you what is the basic like name, or what, how do we classify these types of functions. Now guys, before evaluating derivative for any function, one has to go back and one has to review and recall all the techniques, all the methods, all the different types of functions and things that we have learned, and if we can use any of those or combination of those to actually evaluate the derivative of a given function. So if we try to do the same thing for this, which we kind of did in a way, like when we discussed that power rule, we cannot use the power rule, we cannot use anything that we have done with the exponential functions directly. So guys, then one has to think about or think outside the box kind of and figure out how we can find the derivative of this function. So guys, one of the very useful things that comes very handy whenever we are actually dealing with exponential type of functions, and that idea is to actually use the inverse process of that particular function. Guys, this being an exponential type of a function, right? So what one can do is one can think about using the inverse of an exponential function. And what is the inverse process of an exponential function? Guys, we already know it is called the log function. So guys, one of the things that one can do here to actually evaluate the derivative of this function is to apply the logs on both sides. And we know that if we apply something to the left hand side, we got to apply it to the other hand side, and we can the other side, and that is how we like to sometimes and many times basically simplify or evaluate things. Guys, we did the same thing with implicit differentiation as well. We apply the derivative on the left hand side and the right hand side, and then things start to work out for us. So for these types of examples where we cannot use any of the already formal rules or principles, one has to start by using the applying the logs on both sides. Guys, what I'm going to do is I'm going to, just for making it a little more easier for us to understand and write the steps, instead of writing f of x, I'm just going to say y equals to x to the power x. And guys, right here my goal is to find y prime, or you can also think of that as finding dy over dx, whichever you prefer, whichever notation you guys prefer, that's up to you. So I'm going to apply logs on both sides. So if I apply log on both sides, let me apply the natural log. Guys, we can apply any form of logs, but it is easier for us to apply the natural log, where the base we know is base e. And if I apply it to the left hand side, I will also apply it to the right hand side. Guys, once I have it written out like this, then looking at the right hand side, we already know that there is a nice power rule for logs, which says if I have a log m to the power n, and m and n can be constants, variables, it does not matter, it applies for all cases. Now what happens here in the power rule for logs, you just bring the exponent in the front and you just multiply by the ln of whatever was already here, the ln of that base, which is just x here. Okay. Now instead of working with this function, we are going to work with this function. And if you look at this function, It is much simpler than this function y, because here we see that it's a product of a nice linear function times just a log function. Okay, so from this transcendental, well, this ln x is also thought of as a transcendental function, but we know how to deal with ln of x, but we didn't know how to deal with this x to the power x. Okay, so using just applying ln, applying log on both sides, natural log on both sides, and then realizing that this can be simplified using the power rule for logs. Guys, when I say power rule, I'm not saying power rule for derivatives, I'm saying power rule for logs. And let us quickly recall that log of m to the power n, which is n times log of m. So once we have this, now I'm going to just focus on this and this. Keep in mind, my goal is to find the derivative of y. To find the derivative of y, guys, what I'm going to do is I'm going to now apply the derivative on both sides. And that, I mean, how can I find the derivative from this equation? There's no other way except for actually applying that or taking the derivative on both sides. So if I apply derivative on both sides, and guys, you know, I like to write that step, d over dx of ln of y. And that is also on the right hand side, I'm going to write the same notation thing, du over dx of x times ln of x. Now on the left hand side, and of course on the right hand side, we have to use some methods that we have learned before. And guys, that's what actually also makes this challenging, because now we have to use a combination of several methods to solve this particular, or to evaluate the derivative. So if I apply the derivative onto ln of y, we know that y in turn is a function of x, right? So, but at the same time, we know that the derivative of ln function, the log function, is just the inverse function. So it's going to be 1 over y. But we cannot stop right here. We still have to multiply by the derivative of the inner. That is something we have been doing with the chain rule. Then again with the implicit differentiation, which is basically just using the chain rule also. So it's just multiplying by dy over dx. Guys, this on the right hand side is much easier to deal with because there's no y terms here. It's just a product of two. I consider this as f, this as g. Use the product rule, which is f prime times g plus g prime times f. So derivative of f is 1 times the, I just have to write the ln of x plus, guys, what is the next thing? Derivative of ln of x is just 1 over x, and then multiply by the f function, which is just x, right? So what happens here, guys? This x and this x just crosses out. So it seems like things are going to simplify. So it is 1 over y, then dy over dx equals to 1 times ln of x is just ln of x. So it's ln of x and then plus 1. I need dy over dx. To get dy over dx by itself, I have to multiply both sides basically by y. So if I multiply both sides by y, I get dy over dx equals to, so on the left hand side, when I multiply by y, the y's will cross out. On the right hand side, the y will stay, so it's y times, maybe I can write it like 1 plus ln of x. Guys, it does not matter. You can leave it ln x plus 1, but I like to have constant first and then the log function. So finally, the final answer, since we want to write the final answer in terms of x, if it is possible for us to actually have an explicit formula for y, guys, keep in mind, in implicit differentiation, we were not able to explicitly always solve for y, so we can leave the final answer with y's on the right hand side. But in this case, guys, we already know what the y is. It is x to the power x, so I'm going to just replace that with x to the power x, and then I have 1 plus ln of x. That is the derivative of this function with respect to x. So guys, following through, I mean, doing these steps is not too difficult. All one has to like kind of start with is the right method and not using the power rule right away or any of the other rules. First, applying log on both sides so that we could simplify this, and using the power rule for logs, we were able to simplify this. Once we simplify this, then we know like what to do, apply derivatives, and then simplify, and then isolate dy over dx. Guys, this is number 1 challenge problem. I think I'm going to show you about probably 5 to 10 of these. So guys, keep practicing these. If you need any help, let me know, and I will see you in the next video.